So this is the third video on Rational Roots Theorem, and I'm going to kind of call it here. We're just going to go through another example of finding all the possible roots and then the actual roots. A little less theory involved this time. I'm going to go a little quicker. So if you take a look at this, this polynomial here, it's a fourth order polynomial, which is kind of beefy. And there's no x at the end. The last term is definitely not an x term. So I can't pull out any greatest common factors to make my life easier. That's the first thing you should always check. So we just have to go straight ahead into this. P is going to be factors of 27, and Q is factors of 4. So buckle up. Factors of 27. And remember, here's how we do this. 1, 3, factors of 27, 9, and 27. And factors of 4 is 1, 2, and 4. So first, I'm going to look at just dividing everything by 1. I have 1, 3, 9, and 27. And then we're going to look at dividing everything by 2. So I have 1/2. I don't like this color. Hold on a second. Oh, great. There goes my 2 also. All right. So let's do purple. That shows up a little easier. So I have 1/2, 3/2, 9/2, and 27/2. And my last color that I'll pick, let's go with, I already picked blue, right? Let's go with obnoxious green. So divide everything by 4, and I have 1/4, 3/4, 9/4, and 27/4. Okay, and don't forget, at the very front of this, you have plus and minus. So you're actually going to be entering like 24 answers in this box for all the possible roots. And now, which of those 24 possible roots are actual roots? Well, we're going to have to do some synthetic division to figure this out. So let me grab this guy. Come here. And we're going to come down here and start our synthetic division. So first thing I want to check, what were my first few roots? 1, 3, 9, 27. Okay. So how about positive 1? Is positive 1 a root? Well, you make your synthetic division bar, and we're going to put our coefficients up top. 4, 35, 99, 81, and negative 27. And then you put whatever your root is over here, or the thing you're testing to see if it is a root. We're going to find out if that's an actual root, not just a possible root. Now, before we dive into this and start doing all the math, I just want to point out something. I've mentioned this before. If you use the remainder theorem instead of synthetic division, it's quicker for this particular example, because you can plug in 1 here, and you get 4. You plug in 1 here, you get 35. You plug in 1 here, you get 99, and so on. And you can see that there is no way this is going to be equal to 0. Okay, you've got a bunch of big positive numbers, minus 27. That's not going to 0. So I can rule out negative 1. Okay, that means negative 1, we can scratch off our list. And for the same reason, we can scratch off 2. Because, I mean, look, even if we ignore all this stuff right here, which are all positive numbers, 81 times 2 is bigger than 27. So for that reason, I can rule out the number 2 and the number 3. So 1, 2, and 3 are crossed off our list. Let's go check some other ones, like negative 1. So I don't know offhand. You could use Rational Roots Theorem to figure out if that remainder is 0. But I'm just going to go ahead with the synthetic division here. 4, that makes negative 4. This makes 31, negative 31. We might be getting somewhere here. 68, that's negative 68. Any luck with this? 13, looks like that's no good. Okay, that's going to give us a remainder of negative 47, no, negative 50 is the remainder. So negative 1 is no good. So we've ruled out several things so far. We ruled out all the positive whole numbers because they just get way too big. Okay, those are all gone. And we've ruled out negative 1. So let's check negative 2 next. Negative 2, 4, 35, 99, 81, negative 27. So we have 4 times negative 2 is negative 8. Add those up and we get 27. Oh, this is hard. Negative 54. Negative 45. Multiply it becomes negative 90. That becomes negative 9. Multiply that. It becomes 18. That was close, but no luck. We still get a non-zero remainder. So negative 2 isn't going to work. Well, be patient. We'll get to it sooner or later. And usually in a test, it's not going to be that bad. There's going to be one root that's going to work somewhere early on while you're checking. If you know how to avoid some checks that waste your time, like those ones I mentioned earlier, positive 1, positive 2, and so on. So here's the coefficients. I'm going to work through this again. 35 minus 12 is 23. Times negative 3 is negative 69. That's going to be positive 30, negative 90, negative 9, positive 27. There we go. We got one. So x equals 3 is a root of this thing, and now we can factor it. Well, you know what? Instead of going through the effort of factoring it, we've done that before. I've shown you how to factor. Let's jump right into the next stage, which is making a new synthetic division line right where we left off and seeing if we can get another hit on negative 3 as the root. I'm sorry, I should have written negative 3 over here. That's the root, not positive 3. So you bring these coefficients down for negative 12, positive 11, negative 33, negative 3, positive 9. Look at that. It worked again. Okay, and what we have here is now a quadratic polynomial. This is to be written in the form f of x. Now we just found two roots of x plus 3, or in other words, two factors of x plus 3. And what's left is 4x squared plus 11x minus 3. And I think everyone's tired of synthetic division right now. That was a lot of work. Go through the big X for this one and factor it all the way. This should be quicker. If you remember how this works. 4 times negative 3 is negative 12. We drop down the 11 over here. I need two things that multiply to negative 12. That's going to be negative 11. No. It's going to be positive 12 and negative 1. Those multiply to negative 12, but they add up to 11. So now we say x plus 12, we divide it by the initial coefficient, 4, the leading coefficient, and we do x minus 1. Excuse me, that's minus 1 over 4. Now we move things over. This becomes just x plus 3 because it simplifies. This one does not simplify, so we move the 4 over to the x, and that's the factored form. So in the end, we have f of x equals x plus 3 squared. What's this? Another x plus 3. Great. Times 4x minus 1. So if you want to write that in the tidiest possible terms, that's x plus 3, which is actually a multiplicity of 3 times 4x minus 1. That is how you fully factor a fourth order polynomial.